You recall at the end of last time I was talking about the partition function, so let's continue from there. I'm going to restrict myself to the Potts model and talk about that for a few minutes. So the Potts model is defined in the following way. G is a finite graph and there are spins assigned to the vertices. So you have sigma, you have vertices I and j, and you have sigma I belonging to the set 1 through q, which is just some set of designations for q local physical states that are supposed to be possible at any given point on the graph. I'll call them spins, but they could be charges, they could be various things. And then the energy, so a state is a mapping from the nodes of G to this set I of indices. And then the energy of the state is defined to be the number of coincidences across edges. So I could say that formulaically by taking the summation over the edges of the graph, which I'll denote by ij bracket, delta, Kronecker delta, sigma I, sigma j. So that's just counting whenever they're equal. And that's, by definition in this simplified model, the energy of the state. And so therefore, the partition function is equal to the sum over these states of e to the minus 1 over kt times the energy of the state, and that's equal to the sum over the states of e to the minus 1 over kt times the sum over the edges of delta of sigma I, sigma j. And an exponential to a sum is a product, so I can rewrite this as the sum over sigma of the product over the edges of e to the minus 1 over kt times delta of sigma I, sigma j. So in other words, you get 1 as an element of the product if the spins at the ends of that edge are different, and you get e to the minus 1 over kt if they're the same. So Temperley proved the following theorem, probably somewhere around 1970. He proved that z satisfies the following relationship, that if you had an edge, and this, I was using a notation where I would put a little triangle to mean the rest of the graph, but I'll stop doing it. So when I draw an edge like that, I mean there's some rest of graph attached to the edge. And then his formula is that the z of this is equal to the z of the deleted graph plus v times z of the graph that is contracted. So so when you see this, it meant that this was contracted, the edge was contracted to a point. All right, and v is equal to e to the minus 1 over kt minus 1. So he gives a recursion formula in terms of graphs for calculating the Potts partition function. And of course, you also know that if you had a single node next to the rest of some graph, then of course it will multiply by q, because there are q possible states for this, and it's not connected to anybody, so it just is it's just making a bunch of copies of what you had, as many as there are elements in the index set. So why don't we see if we can see that temporally is correct, right? Um, if you look at this edge, it may be that for a given state, these are different. And if these are different, then there should be no thought of making or trying to make a contribution from the collapsed graph, because there's no way to take that state and make it into a contribution on the collapsed graph, because these two spins are different. You can't combine them and make a contribution on the collapsed graph. Let me draw an example so what I'm saying will be clear. Suppose this is the edge that I'm talking about, and suppose this was assigned 3, and this was assigned 5, and this was assigned 7 from the index set. Well, then, if I form the collapsed graph, I don't have any particular way of assigning a spin there, because I've got a 3 here and a 5 here. But if I had a 3 and a 3, if these were equal, if it was a contributor to the energy, then I would also get a contribution from that graph. I could get a state for that graph. So then think of the two conditions. If they're different, then we think of this as not applying at all, and then this in this graph not having any connection, there would be there would just be a 1 in the sum. Here there's an actual 1 in the sum, and here there's a ghostly 1 in the sum, because you could think of putting a 1 in the sum for every pair of vertices. It didn't matter. You can put as many 1s in the sum as you like. So in other words, I'm saying that in the case where these are different, then the identity is correct. And what if they are the same? Well, if they're the same, then over here in this partition function, you get a contribution of e to the minus 1 over kt. But in this one, you only got a contribution of 1 in the product. Everywhere else, it's the same. But on the other hand, you also got everything else is the same when you collapsed it to a point in that other graph. So you're going to get a contribution of 1 plus v coming out of that. And 1 plus v, as I have described it, is e to the minus 1 over kt. So that's the logic of this formula. And the formula lets you recursively calculate the partition function for the finite graph. And this polynomial, so you get this polynomial of the graph z sub g of v and q, and this is called the dichromatic polynomial. And it's also sometimes referred to as the Tut polynomial. But the Tut algorithm starts in the following. It's a general algorithm that Tut formulated for this kind of thing, which is reformed so that in the Tut polynomial, the formula looks like this, and then different evaluations on loops and isthmus, where in a graph an edge is an isthmus if when you remove it, it disconnects the graph. And of course a loop is a loop. I won't bother you with the details of the Tut polynomial, but this kind of thing can be reformulated so that you have a uniform, simple recursion like that. It just adds up the deletion and the contraction, and then you have some different evaluations on the loops. But we'll stay with it. And this can be reformulated in terms of that, and vice versa. So they're really equivalent. So this was a very beautiful observation of Temperley, which he then and other people continued to investigate Potts' model for a long time, trying to see if they could find the limits for arbitrary Q for, say, some simple geometries like a rectangular lattice of size n by n. But this is still not fully solved. But the formula is very close to the bracket, and so let's see if we can see how the Potts model is related to the bracket. I always get these things wrong. How the Potts model is related to the bracket by reformulating it a bit. So the reformulation I have in mind is the following kind of construction. If we start with a graph, let's suppose I start with this triangle graph, and at every edge of the graph I draw, you've seen this in other contexts this week, it comes up. You draw a little crossing. I won't determine yet whether it's over or under. I draw a little crossing on each edge, and this is a planar graph, so then the configuration of ends here can be connected by just walking around the face of the graph that you see, and that's a well-defined method of connecting these ends, and similarly around this face, and I obtain a four-regular graph in the plane, and in this case you see I get a trefoil diagram. If I take some other graph, I'll get another knot diagram. And knot theorists discovered this long ago in the opposite direction. The opposite direction was you start with a knot diagram and you checkerboard shade it, which can be done by for various reasons having to do with the Jordan curve theorem. You can always two-color the map that the graph makes. And then you put in a vertex for each shaded face and an edge for each crossing, and you obtain a graph in the plane. And so you can go backwards, and so you see this is called this, let me see, from graph to knot diagram, not necessarily crossing specified, is called the medial construction. And from knot diagram to graph is called the checkerboard graph construction, usually by knot theorists. And these constructions were discovered independently by knot theorists maybe in the 1920s, and by people doing statistical mechanics and things later on, and probably by graph theorists as well. But you see, if I wanted to do that, then I were somebody who had the idea that I would investigate the dichromatic polynomial by using the medial construction, then what will that look like? It will look like this, that I start with this is equal to this plus v times that, and I would form the medial construction on these graphs, so I would have this. And now what would the medial construction look like here? Well, you deleted the edge, so it's going to go around like that, and it's going to go around like that. And here you contracted, so it's going to go like this. And so you see that the bracket recursion idea of smoothing in the two ways is actually what happens if you take the medial construction on the take the dichromatic or deletion contraction kind of algorithm and translate it into the medial construction. If we wanted to keep track of things, we could shade these, and then instead of calculating the partition function on on a graph, I could calculate the partition function on a shaded knot diagram, and it would come out the same. So for example, suppose that I wish to calculate the partition function for this. Well, then I could use this instead, which is the shaded diagram, and then this would recurse in the following way, that I would get that this is equal to this plus v times this. You see, oops, where the regions came together like that. And now you see something about how you're going to do the rest of the counting, because by the time you take some knot diagram and smooth it, you will have a number of regions involved, right? Let's see, suppose I just take an arbitrary knot diagram and I checkerboard shade it, and then I decide to smooth it in some way. So I might have smoothed it here, and maybe I smooth this one here, and this one here, and this one here, and that one here, and this one here, just arbitrarily choosing some. And then what evaluation am I going to get of the dichromatic polynomial when I use that? Well, the answer is q cubed, right? That's what's going to come from just that. And then I would have gotten some v's or not, depending on whether I smoothed it one way or the other. But the evaluation of a bunch of regions is going to be q to the number of regions. So I'm counting regions, not circles, when I do this count. So I'd have to recount if I want to write it in the other form of the bracket. That's a technicality, and I'll just show you the end result. But this way, it's counting the number of regions. So the other part of the thing is that z of a union of shaded regions is equal to q to the number of regions. Why the number of regions? Because each region corresponds to one collapsed vertex in the deletion contraction algorithm. There were two vertices here and here, and they got collapsed when this happened. There was one vertex here and it got collapsed to itself, and this one got collapsed to itself. So you see the number of regions is what you're after here. Well, that's fine. You could go ahead and investigate the Potts model on shaded and dot diagrams if you wanted to. Like in this case, we can continue computing and we get q squared plus vq. And that's the answer to the Potts partition function for a little line graph with two nodes. And you can put the v back in and you get the actual partition function. Okay, so then the question is, could we translate this into something which is counting the number of circles rather than the number of regions? And the answer is yeah. A little work with the Euler formula and playing about will get you the following result. So I'll just tell you the result and we'll do an example, and then that'll be it for that part. I'm going to define a curly bracket here, and the curly bracket is going to be equal to the deletion plus v times the contraction, but renormalized by q to the minus 1/2 times the contraction, and the value of a single loop will be equal to q to the 1/2. So that's a bracket. It's not a topological bracket in the sense of being invariant under the Reiter moves, but unless v was chosen exactly right, and then you could push it into that condition. But in general, it's not invariant under the Reiter move, but it's perfectly good graphical recursion, and it's going to be counting the number of loops in the states, not the number of regions. And then what is the result about this? Well, zg is going to be equal to q to the n over 2 times curly bracket k of g, where k takes k of g is a knot diagram that's obtained in the following way. You form the medial construction, and then you put in crossings all of the same type, like that. So if we were to go back to this and form k of g, where g is equal to the triangle graph, then k of g is always put in crossings of this kind, so that the line of the graph is going through the A-type smoothing, if you're used to that, and make them all the same. And if you make them all the same, then you get an alternating diagram, as is not hard to see. You always get an alternating diagram, and so in this case you have the trefoil knot, and this is k of g. So I choose a specific knot because I need a knot in order to instruct me to do this, and that's the knot I choose, and n is equal to the number of nodes of g. Okay, so that's the answer to the puzzle. How do you reform it so that instead of talking about regions, it talks about numbers of circles? And maybe I won't recalculate it. You could have fun recalculating it. What is it you would or we could do it. Let's do it just for the sake of completion. So what is this? That's what corresponds to what I had over there, right? That's k of the little line graph, and this is, according to the formula, it is the evaluation of this guy plus v q to the minus 1/2 times the evaluation of this guy. And this curly bracket, therefore, is q to the 1/2 squared, which is a q, plus v q to the minus 1/2 times q to the 1/2. So that's equal to q plus v. That's not the answer, but I told you it was q to the n over 2. So the z coming up from here, the zg is q to the 2 over 2 times the thing below, and that's q times the thing below, which is q squared plus vq, which is what we got over there. So maybe you begin to believe this formula. Now, there is an advantage of having this formula written in terms of the bracket philosophically, because it says to us that the bracket really is very close to being a statistical mechanics model, right? It's telling you that if you change the parameters in the bracket polynomial from being the usual topological parameters to something else, then you actually are computing a statistical mechanics model. And maybe it's possible to have some better insight into the limit of the Potts model by looking at the limit of the weaves instead of looking at the limit of the graphs. And I don't know. I think new ideas are needed there. But another thing comes out of this, which illuminates something that Temperley did and Lieb did, and that you have heard before about as the Temperley-Lieb algebra, but maybe you hadn't seen this story. You know that if we think about a braid, if we think about a braid like this, then the bracket, of course, is going to give us, in this form, I'll do the deletion first, which was this one. I mean, if I were doing that guy here, I would delete, and then I would contract like that. And you see that this corresponds to the identity in the usual diagrammatic that we're used to for the Temperley-Lieb algebra, and this corresponds to U3. I remind you that diagrammatic Temperley-Lieb algebra consists in, I'll do it for 3 strands, identity, U1, U2, maybe you should do it for 4 strands, U1, U2, U3, and then you have some nice identities in multiplying these like braids. So for example, ui squared is equal to the value of the loop multiplied by ui, and I'll just put value of the loop, depends on where you want to be. Like in this case, it would be q to the 1/2, and then you have that ui plus 1 ui is equal to ui, and that comes about because of this bit of topology here. And they commute if they're farther apart. And so you see that if you had started with something that was a weave, and you perfectly well might, like for example, suppose that you were looking at I don't want to get involved in too much drawing here, but if you were looking at a lattice like that and you made the medial construction, then you would find that having made it, you could re-express what had gone on in terms of braid. And so instead of having the lattice, you would have some braid, and then you would have some condition on the boundary of the braid that would be closing it to calculate the partition function. So if you reformulate the statistical mechanics model in terms of a braid, then the partition function is expanded in terms of the Temperley-Lieb algebra. Well, that statement was made by Temperley and Lieb, but in different formulation. They wrote down matrices that expressed the model, and they found this algebra happening in their matrices, and and they abstracted the algebra and named it. And other people, of course, called it the Temperley-Lieb algebra. But what happens here is that by rewriting it in this form, we see this very useful diagrammatic of the Temperley-Lieb algebra coming out. And so this diagrammatic has been very useful ever since for all sorts of things, including thinking about the Jones polynomial. And so that's one of the nice things about seeing how the Potts model is related to the bracket, is that it allows one to see how the Temperley-Lieb algebra that Temperley and Lieb had defined is actually directly related to this kind of combinatorial structure. There's certainly more to think about there than has been done yet, but if you start looking at the literature, you'll see, of course, that people have been using this kind of formulation of Temperley-Lieb algebra all over the place, as you know. So that was the story I wanted to tell you about the Potts model. But let's talk about arbitrary signs on the graph as long as we're talking about this. Let me take this. This is a not theoretic remark. You could say, well, why don't I translate the bracket polynomial into graphs entirely? Why should I use not diagrams? Not the sort of thing I like, but I kind of like. Why not translate it the other way into graphs? What will that look like? Maybe it will be nice. So then you need to translate the Reiter moves, but I'll come back to that in a moment. But what would it be like to translate the bracket? Well, let me show you how that works. Then, of course, I want to have signed graphs, right? Like the trefoil knot will be by convention all plus, and when I have an edge that's plus, I will draw upon it this crossing, and when I have an edge that's minus, then I will draw the other crossing. And so now, if you take a signed graph and form the medial construction respecting the signs, then you will get back whatever knot you happen to have encoded that way. And you can encode knots as graphs and as signed graphs. So knots and links correspond to signed graphs. Planar knots and links, classical knots and links, correspond to signed planar graphs. So then, how would you translate the bracket? Well, let me show you what the formula would look like in the Tut form. It's easier to do it in the Tut form. It looks like this, but I have a tendency to forget some convention about it. That's the formula. So this is a generalization of the Tut polynomial to sine graphs. So instead of having just plus plus, I have the b and the a for the square bracket, which was expanded a times one smoothing b times the other. Okay, right? Square bracket of this is equal to a times this plus b times this, and I kept my usual convention, which means that the deletion should be corresponding to the b in the plus form, and that's why the b and the a got reversed, and the value of the loop is equal to d. And then because the value of the loop is equal to d and I'm not normalizing it, I need a d here, and that's the translation. And you could have fun with that as an exercise and see that it's right if I didn't make a mistake. So you see, this evaluator here is G is made of loop and isthmus only. That's all it is. It's been contracted and deleted to the point where it's just some loops and isthmus, and then you evaluate it directly. That's the way the Tut polynomial works. This looks just like the Tut polynomial, except it's got these extra signs in it. Well, why do I mention this? Because I got interested in it again. The thing about this is that it's invariant under the generalization of the Reiter moves for graphs. So it isn't just for planar graphs, so it's related to virtual knot theory, but I'm not going to go into it. I just show it to you so that you can play with it if you're interested. And this is how, if you wish to do, one of the ways in which, if you wish to do knot theory without ever drawing a knot diagram, you can translate it into graphs. Yeah. Oh, and yeah. Let me draw a graph with an isthmus and a loop, and then everything will be clear. Maybe we will draw another loop over here. So this guy is an isthmus because an isthmus, like the Isthmus of Panama, if you were to disconnect the Isthmus of Panama, you would disconnect North America from South America. So disconnect the graph at an isthmus. Loops are loops. They are edges that come back to the same vertex. So this would be evaluated without the recursion, just by that formula. So the other side of this story is, what do the Reiter moves translate into if you do it for graphs? And you may have seen this. This also goes back to the 1920s and 30s for knot theory. Take the first Reiter move and shade it, and you see what's going on. I'll try to be economical about writing this. So you see what happens here is that you have a pendant edge labeled plus. So a pendant edge labeled plus or minus can be removed. That's the move, right? Yeah. Here, and now I will draw rest. No, I don't. I will draw rest of the graph. Okay. And then here's what happens if you remove that. Excuse me, I'm getting my colors mixed up. If I remove that, then I have this shading, and I only have the rest of the graph coming up to that vertex. So I won't redraw it, but you see, here's what happened at the graph level. You removed a pendant edge, an edge that just has one end, not connected to anything, right? That's a Reiter 1 move. What about a Reiter 2 move? Oh, well, wait, but there's more to the Reiter 1 move. It might have been shaded this way. Surely it might. And in that case, there's a vertex over here, and it goes around through here, and it happens to be minus. And when we remove, and there's the rest of the graph, and if we undo the move, then the circle disappears. So you can remove loops, and you can remove pendant edges. That's the first Reiter move. And every Reiter move is splitting into two. Let's see the next one. If you have this, and it's shaded this way, then you see that you have two edges in parallel, and one of them is plus and the other one is minus. And if you shaded it the other way, then you have two edges in series, and one of them is plus, and the other one is minus. And you can, now what can you do to these? What happens when you do the move? When you do the move this way, you end up with disconnected regions so that you end up deleting the two parallel edges. And when you do it this way, you end up connecting them together by you end up collapsing this vertex to this vertex, and this disappears, and so it's a kind of contraction like that. So those are the Reiter-Meister 2 moves. Plus and minus in series can be deleted, and plus and minus in parallel can be deleted, and plus and minus in series can be collapsed. And then the third Reiter-Meister move, well, there are two ways of shading that, but let's shade it one way. And you get a star with some decorated signs, which are plus and minus and plus, okay? And if you did the move, sorry, I'm crowding the board, but probably better to do it on this board. So I do this move. Now I wish to shade it in such a way that the shading would extend to whatever diagram I was working with. So that forces me to shade it this way. And then you get a triangle with a plus and a minus and a plus. And there's a pattern to that. So this is a star triangle relation, and if you superimpose them, you see that the edge opposite minus becomes plus, and the edge opposite plus becomes minus. So you switch the signs, and that's the star triangle relation, which becomes the third Reiter-Meister move. So those are kind of elegant moves on graphs. And if you say that two signed graphs will be regarded as equivalent, if you can get from one to another by a series of these moves, why then this polynomial that I've defined here will be invariant under those moves if we make the same choices for A and B that we did for the bracket, the topological choice. So you can formulate the bracket polynomial in the category of signed graphs, but you will notice that the category of signed graphs is actually not necessarily planar, and it's still true. These moves, as described on graphs, don't depend on the plane. They depended on the plane in order to be articulated, but as they stand, they're just parallel connection by plus and minus, or series connection by plus and minus, or star triangle, and so knot theory becomes generalized in that sense to all possible signed graphs. What will you do with that? I started thinking about that again. And there's some relations with virtual knot theory. There's another thing that's worth remarking about this, and then I'll stop this line, and that's an observation that I made with Jay Goldman a long time ago. If you think that plus means conductivity and minus means conductivity, whatever negative conductivity means, conductivity is the inverse of resistance, right? So negative conductivity means amplification. So it's not so easy to make a little amplifier that's exactly the same value as something else, but it's not hard to make resistors. So this is a little funny, but in terms of the graph theory, think of it that way. And then what are the rules for conductivity? If you have two conduits that are parallel to one another, then the total conductivity is the sum of the conductivity of the conduits. So this conductivity of this should be equal to the sum of the plus and the minus. That's 0. 0. Well, that works in general. There's another rule about the conductivity of things in series. It is that if you have A and B in series, then the conductivity of the total is equal to the reciprocal of the sum of the reciprocals of A and B. And that would suggest infinity. But this is infinite conducting. That there's no resistor in there. It's infinitely conducting. And then there's a star triangle rule, which was invented by Mr. Starr in 1890, discovered by Mr. Starr in 1890, an electrical engineer. And this conforms with the star triangle rule as well. So one of the simpler examples of using these moves is that you can calculate the electrical conductivity of the knot between two regions, and that's an invariant of the knot. Okay. So that may be that I said that somewhat in answer to your question, because your question in the largest sense was, well, what happens if we use different signs? And then you see that we can do a lot with different signs. So now I want to shift topics for a very short time, I guess. I was planning to say more about this, but let's see what we can do in a very short time and talk about some aspects of covanif homology. So because it's a very short time, I think I won't mention the algebra very much at all. I just want to show you this beautiful idea and reformulation that's due to Dror that hasn't been mentioned here, and it's worth mentioning. So let me try to explain that by attempting to reinvent covanif homology. So let's see. What is the idea? The idea of the bracket was that you would take a sum of these two possibilities. But the idea of covanif homology was that if you think of the A smoothings as having been uniformly given by the definition by which they are given, then you can think of an ordering of putting the A's before the B's, and then you get an arrow instead of a plus sign. And what happens if you were to change elementary algebra by putting arrows instead of plus signs? I mean, maybe I'd better not go that way. Let me just jump to the usual construction, all right? I have too many playful notions. So let's recall then what happens from that. So you build a little collection of states. So for example, if I was working with Hopflink and we were going to use this, then we take the A state of the Hopflink and then we apply all those arrows that are possible, and we get a big diagram like this. You get a big diagram like that. And in fact, you get a category. So the notion of categorification comes up immediately once you have that idea of replacing something which is equal leveled by an arrow. And here's this category. Well, it becomes a category if I take each one of these to be an object, and I take each one of these to be a morphism in the category, and I will assume for simplicity that the composition of these morphisms is the same as the composition of those, and I will remind you that it makes a lot of sense to introduce the idea that there's a little cobordism that corresponds to each of the elementary morphisms. That is, when you went from an A to a B, that you should think of it as going through a saddle surface like that, so that each one of these is at the top of some surface, and when it goes through the arrow, it goes through a cobordism into the other surface, and when you compose the arrows, you have a composition of those cobordisms, so you're looking across the top at a cobordism from here to here, and I'm not putting in any other structure. So then I could ask at this place, how can I measure how these categories behave when I do Reiter moves on the knot diagram? Right, I'm not assuming that I'm taking homology or anything. So suppose you were confronting that problem. Then you would look at the Reiter move, and let's look at it. And let me draw it the way I had it in mind so I don't change horses in midstream. So then locally your category would look like this. Like that, right. And you wish to compare that with what would have happened if you had pulled these apart and you had the Reiter move there. So where would you compare? Well, the category that happened here ought to be compared into the middle of this, obviously, and then there are things that are going in and out of that we don't know. So there should be some comparison between, let me draw a line, between the upper category, which has this extra objects and arrows, and the lower category, which is very simple. And remember, we're pretending that we don't know what the formulation was beyond this point. So you're looking at this and you're saying, well, how do I map one I would like a functor from one category to the other, but it seems like this object here wants to be compared with this one, and it wants to be compared with this one. And in fact, I see ways to map the individual objects to each other. I can map this one by the identity, forgetting that this happens to have labels and this one doesn't. And I could map this one to this one by a cobordism. I could take it through a saddle, which would do these, and then I could create a circle by using another little boardism like that, create a circle by using another little boardism like that. That would create a circle. And so there is a now sort of natural comparison between this and this, and there's a natural comparison between this and this. But I can't map one. But in an ordinary functor, I can't map one object to two objects. So what do? And the natural answer, with 20/20 hindsight, of course, is that you should form a connected sum object for these two, so that you make a new category up there on the top, and you should form a connected sum object for those two, so that it's only one object. And that would be a perfectly good abstract idea. So then instead of having, up in this category, instead of having two morphisms, one that goes up to here and the other that goes to here, I'm going to have a combined morphism, just as I would to form the connected sum if it were algebraic, which goes to the connected sum object. And you can just do this formally by formally adding things and formally adding maps. And similarly here, the two maps that go out become one map that goes over there. And so I form a new category up there, which is simpler than the other category that I had. And then, in fact, the entire category that I'm going to get out of a given knot or link is going to be considerably simpler, because instead of having piles of arrows going into a more complex thing in the middle and then going on out the other end, I'm going to have object, arrow, object, arrow, object, arrow, one line of objects, one line of arrows. I'm doing what you already know you do. You collapse these all into the ones that have one B, and the ones that have two B's, and the ones that have n B's. And then you have a much simpler category. This category that I'm making contains all the information in the other category in some essential way, because these are connected sums, right? So I've just collapsed everything, but the only maps I'm concerned with in this category are these combined added up maps. So I've made a simpler category out of the other category. But if I do that, then it's possible to compare one category with the other. So that's supposed to have happened here as well, right? So I'll just use the term the chain complex category because, in fact, it looks like a chain complex. It hasn't become a chain complex yet because I haven't assigned any modules to any of these, but if I did assign modules to these, then it's perfectly possible for it to become a chain complex by having these maps, which are the sums, and I'm not worrying about the signs. Think of what I'm talking about as mod 2, then I have this category where the composition of this with this is equal to 0. It will be equal to 0. It will be equal to 0 just as long as these maps going this way, when you compose them, are the same as these maps going this way, and you're working mod 2, because you will duplicate whatever you did in one way with another one, so that when you compose them twice, you'll have doubles. So you get a chain complex category. You get a category which has additive maps and notions of adding the objects. And you can't yet do homology because you can't take the kernels and co-kernels. It's still up in cobordism. And now we can do the comparisons, and we can ask if we but now how are we going to compare, right? Well, again, you can borrow an idea from homology theory and say, I have chain complexes. I can't take kernels and co-kernels, but I can explain what I mean by two chain complexes are homotopy equivalent, because homotopy equivalence means the following, that you would have a mapping from one chain complex, which has its indices, to, now in our case, going back, remember I'm using the usual indexing on the homology, so then I'm using the usual indexing. So this is C0 because it doesn't have any B's, and this is C1 because it has a B, and this is C2 because it has two B's, and we're going up. So when we do chain homotopy in this form, we have to go back down like that, and you want, so a chain homotopy is somebody like this, which has the property, maybe this is the other complex, and then you want that the boundary of H minus H of the boundary is equal to F minus G. And I remind you that this formula is coming from the idea of a homotopy between a map F and a map G, and the homotopy works at the next dimension up. And if you take the boundary of what H does, then it is F minus G top and bottom, and then it is what H does on the boundary and the boundary of what H does. So the boundary of H is equal to F minus G plus what H does on the boundary. That's the idea, and you can and that idea floats up and lives at the categorical level. You can say, I have two of these chain complex categories, and I will call them chain homotopic if there are maps back and forth between them which satisfy the chain homotopy formula. And again, I don't worry about the plus and minus signs. So then the question is, what condition does the chain homotopy equivalence of this to this come down to in terms of the cobordisms that are underlying this? So let's look. If you were going to compare these two, you're going to compare them with, I wanted to use the maps I had here. Yeah. So I'm going to go up by by F and back by G here. All right. And F is doing two things, right? F is going here by the identity, and F is going up here, and up here it goes by a little cobordism that creates a loop and does something like this, and ends up starting down here like that. Sorry if that's illegible. Let's get the other line out of the way. But I'm starting here. I go through a cobordism. I go through a saddle. That gets me this, and then I create a little loop. So we can play with these maps like that to see how they would behave. And that's the F that goes from here up to there. Now, to make a long story short, what I want to do is look at the mapping from this down to here and then back up to here. That's a mapping of this chain complex to itself, and I want to see that it's homotopic to the identity. That's the part that has the non-triviality in it. So that means that we're going to have to think about F, and we're also going to have to think about what the H's should do. But you can see that the simplest ideas will tell you what the H's should do, and we're working on the top line. So what should H do? This is two parallel lines. This has to be let me draw it this way. Create a little loop. Okay, that's an H. And then coming here, I still have parallel lines, but I have to destroy a loop. So it's like that. So you see that the H's and the H's that you would try and the composition of maps that you would try are there in front of you to be tried out, and you can write down what the formula for the chain homotopy should be. And so since I have 5 minutes, that's about what is fair given given that we started late. Let's draw a picture of the different terms in the chain homotopy and see what it looks like. All right. So what is the formula I'm working with? It is I plus, remember I'm mod 2, I plus FG should be equal to boundary H plus H boundary. Boundary maps are also obtained by smoothing or resmoothing along an A, right? And so I'm going to write this down, and then we can stare at it. I was going to use the slideshow, but I think it actually is okay to just draw it. So here is the identity map. And I'm talking about the upper guy, right? I'm only working on the upper line, and the upper guy is a circle between two curves, and there's the identity map. Now, what about FG? Okay. All right, so this is going down, and first I do G, and then I do F. That's F, G, and then F, right? And G into the is going from the upper one down into the lower one and kills a loop, and then we end up with this middle part, which is two parallel lines. That's down in the bottom, and then we go back up by F, which creates which creates a loop. We started here and we ended up creating a loop. So that's GF. And then this should be equal to boundary H and H boundary. Now, let me draw them. And hopefully persuade you that I've drawn them. me draw the other one as well, boundary H and H boundary. Drawer explains this a little differently. He gives you the rules first. I haven't given you the rules. I'm motivating the creation of the rules. So let's see. This is supposed to be first do H and then do a boundary, and this is supposed to be do a boundary and then do an H. So let's see where we're talking about. Where can we do an H and then do a boundary? That's over here, H and then do a boundary. So we start with circle in the middle, and we do the H, which kills the circle, and then the boundary is going to take the right A and smooth it into a B. I'm sorry, the left A and smooth it into a B, which produces a circle. Left A smoothed into a B produces a circle at the bottom. So that's H boundary on the left-hand side. Now what about H boundary on boundary H on the right-hand side? First we do a boundary, and that boundary is on the right-hand A, which is smoothing into a B, and then I do H, which creates a circle. So that's the formula for the chain homotopy, and this formula is supposed to be true. Well, it's not true in general if we're just talking about cobordisms, so we'd like to make a rule by which it would be true. And that's where Drawer's very beautiful insight comes in, because of course, he doesn't say this in his paper, but presumably this is how he came about it. But I think if you ask him, he might say he did it some other way, for all I know. But this is an attempt at reconstruction. So Drawer's rule is, let's consider 4 bits of surface that are surrounding a central bit of space here. Then you can think of adding tubes between pairs of them, and let me number these in the way that is most convenient for these purposes. I will call this one 1, and this one 4, and this one 2, and this one 3. And then you will notice that we have tubed from 1 to 2 somewhere here. Only one tube has been added, 1 to 2. All right, I'll write it, 1 to 2. In this one, we have tubed between 3 and 4. And in this one, we have tubed between 2 and 3. And in this one, we've tubed between 1 and 4. So you could rework the pattern into a slightly more algebraic pattern by saying, I have 4 bits of surface here, and I will label them 1, 2, 3, 4 cyclically around, and then I get to tube between 1 and 2. And I will put the signs that actually end up being the signs that you want. Then you will, when you finally get to signs, then you will tube between 2 and 3. Here, then you will add in tubing between 3 and 4. And then you will subtract off tubing between 4 and 1. And call it 0. So that's called the 4-tube relation. So you're looking at one depiction of the 4-tube relation here, that you would have, if you have somewhere in a cobordism some surfaces near one another, then if you have tubes between them, you're allowed to do that. And so then the theorem is that if you stay at this categorical level and you mod out the cobordisms by the 4-tube relation, meaning 2 cobordisms are equivalent if you can get from one to another by homeomorphisms, leaving the ends fixed, and doing some 4-tubing if you care to, why then the resulting abstract categorical theory of chain complex up to chain homotopy is an invariant of the knot up to the usual grading shifts. That it really works, that it works for the other moves and everything. We've made it invariant under the second Reiter move by doing this, and that's sufficient to make it invariant under the rest of the moves. So This tubing relation follows from using the Frobenius algebra or algebras that you might have been working with this week, like you've been working with the original Kovanov algebra, and you've been working with the Lie algebra, and maybe you've been working with some of the other algebras, but those algebras have the property that they satisfy the four-tubing relation when you map the cobordisms into the algebraic picture that you get from the Frobenius algebra. So then you can calculate homology and so on, but you can philosophically say that Kovanov homology is the abstract chain homotopy classes of the categorical chain complex associated with the knot. And that's at least a nice intermediate conceptual formulation of the theory. You can kind of understand from the beginning why it's invariant that way. One would hope to formulate an invariant in such a way that it's invariant from the get-go, like singular homology is invariant from the get-go. So that's an intro to Dror's point of view, which I think is very beautiful and probably will have further consequences, I hope. I'll stop there.